Well, that was an effusive introduction, I have to say. And that hot pepper was many years ago, so no one has rated me for a long time. So I am a computer vision guy, okay? So I'm not sure, I would say that so there are definitely links to cognitive science, but this is gonna be a pretty hand-wavy kind of talk about computer vision in general, and then how it specifically relates to visual effects like you see in Hollywood. And this is more of a, I would say, hobby of mine than a research area, although some of what I do for research I'll talk about at the very end. And like he said, I wrote a book on this kind of topic just recently, so this is kind of like the advertisement for the book, and I'm teaching a course hopefully on this topic in the fall, and so if you're interested in what you see here, we'll delve down into the nitty-gritty of all this in the fall in my course. Okay, so first of all, I want to talk a little bit about computer vision in general, okay? So computer vision, very broadly speaking, is the study of how to develop algorithms that can help understand images of the world in the same way that people do, right? And so parts of that problem are well studied and have good solutions, and parts of that problem are extremely hard. And so to start with, let me just show you one image. It's gonna be on the screen for not very long, okay? So I wanna see what you can get from this image in the 2 or 3 seconds that it's up. Okay, so let's start out with some questions. So about how many people were there in that picture? 15, 8, 20, wow, okay. How about, where was the picture taken? What kind of a space? Office, bus station? Lab, okay. So who was in the picture? Obama, okay. And so what was kind of the context of the picture? What was happening in the picture? He was stepping on a scale, right? And so, and what was the reaction to people to that event? Like, why was that picture taken? Like, why is it interesting? Obama lost weight, maybe, yeah. Someone else, all right, so someone else was standing on the scale, he was tipping his foot out. Okay, so here's the picture again, right? So you can see that, not everyone got all the answers right, but we had a general consensus pretty quickly of what was happening from maybe just a few seconds of looking at it. And of course, if I had made this picture full screen, you guys would have been able to answer all those questions pretty quickly, right? And so this is, I think, a very good example of the ability of the human visual system to look at a scene and immediately infer lots of stuff with it, right? So for example, you look at this and you see some hues, right? There are these vanishing lines and parallel lines, and you can immediately tell this is in some sort of an office building or a man-made corridor and not, out there in nature or something like that, right? You can quickly say, okay, there are about, so there was definitely an overestimate in this room about the number of people, but, there are about 5 people in this scene, and, if you look at this for more than a couple of seconds, you can immediately rule out these people as not being extra people in the scene, right? Because you can tell that these are mirrors of, even if you necessarily, you see this guy, is like this guy from a different perspective, but you can immediately say, okay, all this stuff here, I can kind of rule out as extra people, right? So you see this thing, which was identified, right, as a scale, but if you think about, if I was to blow up these pixels, right, I've got kind of like this white bar on a white wall background. I mean, there really aren't that many pixels on this object for you to be able to kind of conclusively tell if this is what you saw out of context, this is a scale, right? So again, maybe you're using some sort of a inference that because this room has this tiles, maybe it's like a hospital or a locker room, and that's the kind of place where a scale belongs, so it's more likely to be a scale and not a refrigerator, right? That's also white and could be on a wall. And then there's a lot more subtle things, right? So if you think about how many pixels make up the foot on the scale, again, the pad of the scale is black, this guy's shoes are black, the other guy's shoes are black, right? The number of pixels that make up the foot pressing on the scale is, again, very small, right? And then you make some inferences about kind of why it's funny, right? So like, this guy is looking at the scale, so he can't see the other people kind of laughing at him, right? That's one of the reasons why it's funny, right? You can see everyone's kind of smiling, so you get some sense that something is amusing about this picture, but to infer it's because the guy is looking down and the foot is on the scale, I mean, that's a very high-level cognitive process. And of course, because you've seen him so many times, you recognize this is President Obama, right? That's one of the most obvious things that most people probably picked up on, right? So putting all that together involves a lot of computer vision, and it involves a lot of, it involves a lot of cognitive science and image processing in your head, And to try and reach those same conclusions would be the domain of a computer vision algorithm, right? So for example, at RPI, I teach classes on image processing and computer vision. And the distinguishing thing I would say is that image processing is more like the kinds of operations that you would do in Photoshop to make your picture look better, changing the contrast and cropping out the rectangle that you care about, rotating the image. How do those processes work at a low level? Computer vision is more like a higher level of trying to understand what's going on in an image. And to that extent, it's much more involved with cognitive science. Now, in the very beginning of computer vision research, a lot of it was informed by kind of cognitive models for how the human visual system works and how people see. But I think it would also be fair to say that these days, a lot of computer vision research that has been very successful in understanding images of the world is stuff that really doesn't even have to do at all with how humans perceive images. It has to do with huge data mining problems where for example, if I want to learn to recognize images of a car, I show the computer, 50,000 images of cars, and then maybe 50,000 images of things that are not cars, and I kind of ask the computer, well, can you develop a car and not car classifier, right? And that process really has very little to do with the way that humans do it, but you can still get algorithms that work very well to do it. So I thought I'd just start off by talking a little bit about what are some kinds of things that you would study in a computer vision class, and what kinds of problems is computer vision good at solving right now. So one thing that everyone always maybe thinks about is like CSI or 24, where you have some suspect and you have this crappy image and the person says enhance, and you get this beautiful image of the person, right? So this is kind of like, this is a few years ago. So this is one example of a research project that went from these blurry images to these refined images. You might think, hey, this is like CSI, right? This works pretty well. But again, this was a very restricted problem where you can see all these people are looking straight ahead. They're on a white background. There's probably lots and lots of training data here. Kind of the state of the art in real world kind of super resolution is probably more like this. You got the top row is kind of like the 7-Eleven surveillance camera, and the bottom row is maybe what you could do to make that a little bit cleaner, right? But you're not going to be able to zoom in on this guy's eyeball and see the reflection, right? There's definitely a ways to go in terms of that. But this is kind of like, I would say this is a problem that is more like an image processing problem than a computer vision problem, because you're not really trying to understand what's going on. You maybe could do better if you said, okay, I'm going to try and fit a face model or a head model to this person and try and make their head look a little bit sharper. A big application of computer vision is in what I would call generally biometrics. And so everyone has kind of heard of face recognition. Certainly, my computer for many years has had a thumbprint or a finger swipe to log me in as opposed to a password. So recognizing the fingerprint that is scanned in and comparing that to a database of fingerprints is kind of like an image processing and computer vision problem. There are lots of general human identifiers like your face, your fingerprints, your handprint, your iris is used in, or retina even, is used in very high security environments like military installations. They'll have you put your eye right up to this somewhat invasive device where they shine light into the back of your retina and look at the pattern of blood vessels there. So again, that kind of matching problem, having a huge database of kind of people who are allowed to use the system and matching you to that database using some sort of biometric signature, that's a computer vision problem. I would say that in terms of how successful these problems are, fingerprint I think is good. Iris and retina are also very good. Face recognition is still a long ways off. I mean, I think that despite what you see on TV, they have tried to deploy kind of large-scale face recognition systems. For example, like many years ago, they tried to do something, I think at one of the Super Bowls. They tried to take a database of bad people and the 50,000 or whatever it is people that come to the game and try and find those people as they move around. That problem apparently was totally unsuccessful. So finding people, and I'll show a couple more examples of faces and why that's a hard problem in a second. I guess I talked about blood vessels. So here's an example of, again, if I've got a bunch of pictures of the same environment or the same scene and I want to put them together into one big picture, that's kind of a computer vision problem. How do I stick these images together in a way that looks good? And it may be that I don't necessarily scotch tape them together rigidly. Maybe I have to warp them or deform them a little bit in order to make them fit really well, right? And so this is kind of similar. Like these days, your digital camera probably has a function for panoramas, right? Where you stand in the same place, you take some pictures like this of the Grand Canyon, and then your camera or the software that comes with it will stitch that together into a very nice looking seamless mosaic. Again, that works very well. I mean, as long as you don't move around a lot when you're taking the pictures, then you can get very nice, stitched images. Tracking of objects is a big problem in computer vision. So here, this is an example of putting boxes around people as they move, and this is an example of tracking cars as they move down a roadway, right? And this kind of thing is used all the time. You know, here this is work that this is both work that one of my students did a long time ago for, you know, this has been deployed in freeways, right? Where you say, okay, I want to know how many cars are passing this line every second, and I can use that for modeling traffic flow, and maybe that's how a system like Google Maps knows how busy a certain road is to color it red or yellow or green, right? So that stuff is fairly mature. Then let me talk a little bit more about faces. So this is some work from Carnegie Mellon from many years ago, so things have only gotten better since then. Here's an example of, you know, seeing a person and automatically kind of fitting a face model to that person, right? You can imagine that this would be good for detecting things like the direction a person is looking. So systems like this have been installed in cars. For example, Professor G in our department had a project which I think was with Honda, where he basically was installing cameras near the rearview mirror, and if the person kind of starts to kind of doze off if they've been driving for 12 hours straight, then the system will alert them to wake up, you know, by looking at where they're looking. And so you can see this looks pretty good, and then once you've got this little blue mask, you know, stuck to someone's face, you can actually keep it stuck to their face, right? So here's an example of, you know, this guy's moving his head around, and you know, that mask is really stuck right onto his face, right? And you can imagine you could do something like this for, like, you know, lip reading, for example. If you wanted to design something that kind of tries to look at the shape of someone's lips and figure out what they're saying, this would be the first step towards that. But let me just say that, you know, this is far from ideal. You'll notice that these were all men, right? None of them were wearing glasses. None of them had facial hair. They were all in front of this kind of stark gray background. None of them were trying to purposefully kind of occlude their face, right? So in the real world, you never get video that looks like this, right? This is only for people who are kind of performing for the camera, right? Maybe you could afford to do this again in some sort of secure installation where you have someone walk right up to a video screen and, you know, look right at the screen. But if your goal is to detect bad guys who are walking through the airport, you're not going to be able to use a technology like this. So here's an example. This is like early face detection. Uh-oh. So you see a lot of face detection algorithms that are validated on pictures of groups, right? So you see lots of pictures of cast photos from Star Trek and stuff like that. So here, you know, so this is an example of finding lots of faces in crowds, but again, it doesn't always work, right? So for example, you know, this guy up here hasn't got a face, probably because he's wearing glasses. Who else? This person here, maybe their hair is too low, so they can't get a face. This person maybe is too occluded. This person's face is a little bit off. This person has two faces, not so good. And here's a face over here in this person's pant leg, right? So you have these kinds of, you know, false alarms and double detections and stuff like that. And finally, another big medical imaging problem relates to image segmentation, right? So I had a big project with medical physicists, people who work on radiation therapy treatment for people, in automatically outlining organs in things like CAT scans, right? So you go to be treated for cancer at a hospital, somebody has to manually take the CAT scan that they obtain and outline each of the, you know, not only the organ where the tumor is, but also all the organs where you want to avoid sending radiation, right? That's a big problem. And so here's an example of, you know, maybe the blue outlines are the outlines that a doctor or a resident has manually drawn. It maybe took them half an hour to go through these things and do that. And the red outlines are the algorithm's guesses as to where the objects are. And so our approach here is, you know, to save the tedium of a person doing the same repetitive task over and over again by throwing kind of machine learning at the problem. So we obtain lots of examples of contoured organs, and then we try and learn, well, what do these organs look like across the population? And then for a given patient, how do we fit our model to wrap around those organs accurately? And then we can tell, you know, how often did that agree with the doctor, right? So those are the kinds of problems that we definitely study. So again, if you take a computer vision course, you'll learn a lot more about the guts of some of these problems. So I've been teaching, you know, image processing, computer vision for many years, and I don't know if any of you know this SIGGRAPH conference. So SIGGRAPH is the main computer graphics conference every year. And I have a friend who's published in SIGGRAPH. He goes every year, and he's been telling me stories for 10 years about how awesome SIGGRAPH is. And so there were always all these papers in SIGGRAPH that I thought were really cool. I liked the results, but they didn't have anything to do with my research. And I couldn't really find a way to justify my going to SIGGRAPH just to see these cool papers, basically. But then I started to kind of see a common thread, which was that a lot of, first of all, SIGGRAPH publishes not only computer graphics, but these days a lot of what they publish is what I would call computer vision. And a lot of the cool effects that they were looking at, number one, they were related to Hollywood, visual effects, which is something I have kind of an amateur interest in anyway. And number two, they really, at heart, are the, kind of extensions of the kinds of things that I teach in my classes. And so what I wanted to do was to write a book that kind of bridged the gap between the stuff that I teach in my class and the way it actually works in Hollywood. And of course, some things are very similar and some things are very different. And so that's really the meat of what I want to talk about today. And then, of course, you can ask me all sorts of questions here and at the, after the graduate student session later. So I guess I can stop for a moment and ask, are there any questions just about general computer vision, about what it is or why you use it? Yeah?
Could you talk a little bit about how sort of bottom-up versus top-down contribution?
Right. Yeah, well, that's kind of a big division between, not division, I mean, it's not like a, schism in the community or anything like that, but I think that a lot of computer vision started with kind of a top-down thing, like principles of perceptual organization, right? How you, like you might try and say, okay, I'm gonna find a building or a refrigerator by finding lines in the image, and I'm gonna try and say, okay, these lines connect up into faces, and these faces connect up into cuboids, and I'm going to try and say, okay, these cuboids should be like this. And so that's kind of the way things started, I would say, maybe in the kind of 80s, was a little bit more top-down stuff, drawing on principles of the way that humans process low-level vision in humans, basically. But, since then, and especially with all the computational advances of being able to collect just tons of data and be able to do these massive algorithms, massive training algorithms, suddenly it became much more practical to kind of just throw computing resources at the problem. And so, for example, now the way you might solve an object recognition problem would be to say, okay, like I said, here are a zillion positive examples, and here are a bunch of negative examples, and the basis for deciding whether the object is present or not is based on small little squares of pixels that individually don't really have any perceptual obvious significance, right? Just little corners of, so if any of you have done any computer vision reading, you may have heard of what are called SIFT features, right? SIFT features are just like little groups of pixels that individually are kind of unremarkable, but then you say, okay, well, here is this shape, and I notice that I see this shape, 95% of the time in cars and 5% of the time in other things, right? So this is a kind of a discriminative feature, even if a human would not really recognize that as something that's really interesting. And then you kind of, okay, so then I'm looking at a vast collection of these features, and I see which ones I find in the image, and if I find more than X of them in my car class, then I call it a car, right? So, there definitely has been, I would say that in some communities, like object recognition, I think it's now very bottom-up, Now, in terms of really understanding what's going on in image, like why is that Obama picture interesting, that maybe you have to go back to kind of a perceptual organization about thinking, okay, gaze angles of these people, estimating those in the scene, and this guy's looking that way, and these guys are looking this way, and that's kind of much more of a top-down thing, in my opinion, right? So there is, it kind of depends on what the kind of problem that you're trying to solve. Yeah? Oh, yeah. So that's all totally in the same domain. Everything I showed here was still images, but I'm going to show video in the rest of the talk, and that's for sure like the extension of a single image to multiple images, and that, of course, is a harder problem, right?
Well, but then you can ask the same question, like you can kind of a bottom-up approach where you analyze each image and then sort of put it together, or you can
Right.
look for habits temporally.
Yes.
From the top down.
Right, and again, yeah, well, there's, again, a lot of it comes down to the problem you're solving and the constraints you have, right? So for example, you could always theoretically do better by looking at the entire video sequence as one big piece of data and trying to find out what's going on, right? But realistically, a lot of times, for example, in a tracking scenario, you don't want to keep the entire volume of data around to make a decision about whether someone is present in this frame, right? So maybe you have a lag and you say, okay, I'm going to look at the last 5 frames and use that as my memory for the purposes of a tracking problem, right? So yeah, it's the kind of thing where sometimes you're forced to do kind of image by image processing independently in order to just get something that works in the constraints of your problem. And of course, the more time you have, but then you run into things like memory. Can I possibly store an entire video sequence? So right now we're doing a project where we're basically talking about fundamentally a week's worth of video data, right? And we've got to find a way to break that up into manageable chunks, right? So Yeah, I mean, I definitely have done stuff where it's image by image, and I've done stuff where it's more like, you know, for example, I did a project on basically detecting whether people are moving with the crowd or against the crowd, right? And for that, we look at the entire person trajectory before making a decision about whether it's in the with crowd or without crowd, right? So for that, there's much more of a time lag in making a decision, but you can do a lot better than if you were to do it on the spot, right? Yeah, so, yeah. Hmm. Right. Well, I mean, so I would argue the vision is not really up to the task of interpreting that image the way that a human does, right? I mean, it could probably get you as far as saying there are about 5 people in the scene. Computer vision could probably also get you about as far as saying that they're in some sort of a man-made thing. But in terms of getting the joke, computer vision is not gonna get the joke, right? They'll probably be able, you could probably estimate the head directions of those people, but on top of that, then you'd need some sort of a, you know, you wouldn't be able to put together that inference of guy looking this way, people smiling, you know, this is a scale. All that stuff is much too complicated for some automatic algorithm to come up with the answer. So that's a place where we can't do it now, and I really doubt that we'll be able to do it in the near future, right? I mean, that's just too hard. And so in some sense, it's amazing that, you know, people can do it so quickly, right? I mean, even if you showed that to somebody who didn't know who Obama was and didn't know what a hospital was, they might be able to still get the joke, even if they had never seen it before. So that's a place where we won't be able to duplicate humanity, I don't think. Yep. Right. Yes. Right. Yeah. Yeah. Oh yeah, it helps you for sure. And in fact, I mean, that's a problem where you really can't do it from just a single image, right? You need to look at the whole motion of things as they move past, right? So in that case, you know, you definitely are keeping track of motion vectors between cars. And I think that, you know, actually, so part of that is involved in what's called optical flow, which is, right, you know, and that's, I think that you probably already used the word optical flow in cognitive science, right? You talk about, you know, the human visual system, right? So we're, in computer vision, also interested in accurately estimating optical flow. And sometimes that's easy, and sometimes that's very difficult, right? So if you're moving the camera, you can use optical flow very well to determine the direction the camera is moving. If you are observing a crowd of people and they're all moving around, you know, in a clump, it's very difficult to use optical flow to tell how many people there are in that crowd, right? So there are definitely limitations. So yeah, but optical flow is a key tool for sure in lots of vision algorithms. Right. Yeah, yeah, the first down marker, right. Right. Yes. Yep. That's a very, yeah, but that one reason that works so well is it's a very constrained problem, right? Because so one thing I didn't talk about here, but I will talk about next, is camera calibration, right? How do you know where the camera is in relationship to the field, right? You have to have that very, very precisely. And in fact, apparently, they have to go to the extent of really doing a detailed survey of the field, not just modeling it like a flat surface. They have to note that the surface is slightly bulgy in the middle to let rain run off or something like that, right? So every stadium that has that technology, they really have to work hard to make it work. But now, yeah, so that came into being kind of when I was a grad student, and now it's really mature, right? Now you see it everywhere. You see not only the first down line, but you see things that appear to stick to the field or stick to the stands, right? Right. And so I'll talk about that. That would be, in terms of visual effects, a problem that I would call match moving, which basically means how do you estimate how the camera's moving in such a way that you can put stuff into the world that looks realistic? And the first down line is one example of that. Okay, so let me talk a little bit about visual effects, right, which is what we all came here to see. So, so a little bit of context is that, you know, I spent, you know, a year reading, you know, SIGGRAPH papers and CVPR papers and putting together what I thought was kind of the academic side of things. And then I went to Hollywood for a couple weeks, a couple of years ago, and spent some time with people in the visual effects studios who make, you know, the effects for these movies, and kind of had a list of questions trying to get them to give me some sense about how these algorithms that I had read about, you know, in the lab related to what they do in real life. And some of them were really totally unrelated, and some of them were very related. And so that's kind of what I want to share with you now. Okay, so the first problem I want to talk about is called matting. Okay, so fundamentally, every image that you see in a movie, even movies that you might not think are visual effects, you know, stories, is probably the composition of many different elements, right? And so oftentimes, those elements, for example, are people that are pulled off of a blue screen or a green screen, right? So you guys have probably seen, so for example, you know that the weather forecast, right? The guy who's giving you the weather is standing in front of a green screen and the map is put in behind him, right? So this is fairly mature technology, right? But this is used on a regular basis in Hollywood. And again, some good techniques for this exist. So the basic idea is you want to take everything that is not blue and replace it with some other background. So this is a picture from Tron Legacy, right? So this is the original scene, and this is what it becomes, right? And so you might think that this is a fairly straightforward problem, and it is pretty straightforward, but not so straightforward that you can just automatically do it and never look at the results again, right? So from a computer vision perspective, what things are easy and what things are hard? Well, so things that are easy, kind of, for example, this guy is wearing this black bodysuit. So there's like this very strong black line between him and the blue background. And so you might think, okay, well, it's pretty easy to say, okay, if a pixel is really blue, more blue than anything else, just call that the background, right? And that will work for things that have really sharp edges. But where you run into trouble is stuff like this, where you've got this kind of, here this guy is blurred, and this ring is blurred because of depth of focus, right? And so, or depth of field. And so every pixel here is actually, like here you can see that there's some stuff that is part of this guy's leg, and there's some stuff that is part of the disk, and that makes up the color that is at that pixel. And again, the human visual system is very easy, or is very good at distinguishing, hey, this is the figure and this is the ground, right? That's a very perceptual organization kind of problem. But now the computer vision algorithm is in the position of having to say, okay, this pixel here, it's mostly white, but there's some blue showing through, and that blue comes from the background. And it's very important to know what that mixing actually is in the foreground so that you can only pull the foreground off with its true color and put it on a background and make it look good. If I was just to kind of crop a scissors around this thing and say everything inside my hole is everything inside my hole is the foreground and put it down in a background, you're going to see blue stuff bleeding through because I'm picking up stuff from the background that shouldn't be there. So I have to estimate not only what pixels make up the foreground, but also what fraction of every pixel corresponds to foreground, right? So stuff like this, picking up the soft edge of this guy or the soft edge of this ring is pretty difficult. So one example I saw when I was there a couple years ago was the Muppet movie, right? They were just doing stuff for the Muppets. And so they had this blue screen plate of the Great Gonzo, and he's falling from a building, and really the way that actually works behind the scenes is there are like 5 blue-suited masked puppeteers with blue sticks that have different parts of those sticks attached to Gonzo, and they're waving these sticks around to make him look like he's flailing in the air. And all that stuff has to get, detected and painted out, right? And so you've got, and because you've got all this frenetic motion, that motion blur is going to basically be the same kind of thing as this, where you have to figure out what mix of every pixel is foreground and background. So the way these problems typically work is that you will have an expert artist who has some, years and years of experience and knows, okay, for a picture like this that is blurry in this way, I need to apply this kind of blue separation algorithm that I know has worked for me in the past. So there's a lot of human experience that goes into solving that problem. And maybe that will get them 90 or 95% of the way there, but then they have to kind of work on the parts that don't work very well and kind of find an algorithm that will work well for them in those areas. And then the big problem is pushing that mat forward into the video sequence, right? Because you don't want to solve this problem on a frame-by-frame basis. You want to have something that works for the whole video, but it could be that, again, due to the way this video moves, it's maybe a tricky problem to get something that works across the video sequences. So you may have a series of pieces of algorithms that are working in different parts of the image and for different parts of the frames in the shot to make something that will work well. These effects artists don't want to do something that is like painting out manually every pixel in the image independently. That would be a huge amount of work. But there is a massive amount of human effort in this problem, even for blue screen and green screen shots. So much so that is really, I wouldn't say the lion's share, but this problem is just solved by thousands of artists in Hollywood and around the world every day, just picking people off of blue screens in a way that it looks good. Again, some of you think, man, this should be just like an automatic problem, but it's really not super automatic. Here's another reason why things are complicated. This is an image from source code. So here, you've got this kind of wispy blowing hair, right? And to separate out that hair from the green screen and to remove the green component that you can see through this blowing hair, that's a pretty tricky problem, right? And also there's a little bit more complication in the sense that here these people are kind of backlit, right? So actually there's a combination of the foreground color the green screen and this rim lighting, you know, that is not really, so even modeling the mix of these pixels is tricky. Yeah. I don't think that there's a really big reason. I mean, you see green screen and blue screen kind of interchangeably in behind-the-scenes pictures. A lot of times it's as simple as, you know, who they know as a vendor and who can get them a screen of that size and shape that they need, right? I think that green is, yeah. I think the quality is about the same. I mean, so basically, you know, one of the reasons generally for the color is they want to find something that is as different as possible in human skin tone, right? So they don't want to use a red screen. That would be really bad because skin of all colors has too much red in it to be useful, right? Whereas there's very little of this green in anyone's skin, right? So I would say that, you know, in my, you know, brief experience, I think that green is kind of becoming more common than blue, but I don't think there's a real reason to prefer one. Yeah.
That point, one of the points made about that is green is close to the middle of the visual spectrum. That means there's less directly into lenses. Whereas
Yes.
blue, you might be incorrect or chromatic aberration.
Yes, that's a good point too. That's a good point, yeah. So let me just say that, you know, obviously in a science fiction movie, you're used to kind of assuming that people are on green screens, right? Obviously they're not in these fantastic situations. They didn't put these actors in front of this explosion, right? But there's a lot of cases that the, you know, even for movies or even lots of TV shows are shot on blue screen these days. I'll show you a couple examples where, you know, you take a thing like this. This is a frame from Zodiac, right? David Fincher movie about, you know, a serial killer. You wouldn't think that's a big visual effects show, right? But here, you know, these guys are basically this guy, okay, point at that X over there and we'll fill in this building later, right? And this has only gotten better and better, right? To the point that I would argue that it's almost imperceptible. I'm gonna show you some videos in a second that should make the point for you. Oh yeah, I'll show it to you right now. So here, for example, is a show reel from a company that produces effects for TV, okay? And so you're gonna see shots from shows like Grey's Anatomy and Ugly Betty and stuff like that. All right, so I'll play this without comment. All right, so let me show you this. This one just blew me away the first time I saw it. Right, the guy wasn't even there, right? The guy in the booth. I just want to show this one more time. I mean, you know, you wouldn't have thought anything about this shot, right? Right? And so the reason for this is pretty simple. I mean, a lot of it comes down to cost, right? I mean, these days, to film somewhere real, like on the streets of New York City, right, you need to get permits, you need to close down streets, you have, you know, gawkers who are looking at what's going on, right? I think that it's safe to say, I mean, and now you can start to look at your favorite TV shows, but I would argue that almost every TV show shot that appears to be outside is probably shot on a green screen, okay? And you can start to see which ones are good green screens and which ones are not, right? Like what was I watching? Probably stuff I shouldn't admit to watching. All right, so I really should admit to watching Smash, right? I just flipped past it last night. I was academic curiosity, and there are people having a conversation in Times Square, right, at a cafe in Times Square. And I am 100% willing to bet that no matter how good that shot looked, they didn't block off Times Square for people to have this conversation at a cafe table, right? But you don't think twice about it anymore. The green screening has gotten really good, and it's gotten to the point that you don't need to hire like Industrial Light and Magic to do this green screening effect. There are lots and lots of small companies in Hollywood and elsewhere that will basically, you know, do all these kinds of effects for a certain show. So for example, I was talking to people in Hollywood who did all the effects for like Bones, for example, you know. And a good reason for doing this also is, you know, many shows are shot, well, most shows are shot in Hollywood, right, in Los Angeles. and they look like they're in Boston or Washington or whatever. And there are companies that will basically sell you what they call the virtual backlot, which is, they have the ability to recreate New York or Boston or San Francisco from lots and lots of real video footage that they can match up to the footage that was actually taken on the green screen, right? So, for example, Bones is set, I think, in Washington, D.C., right? So they do lots of green screening where they will replace, the L.A. Metro with the Washington Metro, and they'll put the Capitol in the background and stuff like that, right? So, so now you can kind of start to watch for green screen stuff. Some of it is really obvious and some of it's not. So at this point, these are shows that are, at least 2 or 3 years old, right? So now it's a very mature technology. Now, it's even harder, though. I mean, there are times, and many times, when you don't actually have a green screen, right? So for example, Clint Eastwood was apparently very passionate when he was shooting this movie called Flags of Our Fathers, this kind of World War II movie, about not having green screens everywhere because he felt like it would detract from the actor's experience, right? So you got a picture like this that you want to turn into a picture like this, right? And so that is a much, much harder problem because now there is no pixel color that is like super clearly background, right? And that separation problem is now much more difficult because if you look, for example, here, the brown of the rocks and of the train is really not that much different than the brown of the color around this person, right? And so this is a case where really you are talking about a human very carefully outlining and then estimating the blur across every edge in this scene and getting it right so that when you pull the sky off the background, you don't really perceive the difference, right? And that you can throw hundreds of person hours at to solve this problem. There are lots of people working in dim rooms in Hollywood doing stuff like this. And so, if at all possible, they want to throw up a green screen behind a person to make that separation problem much easier, but sometimes you just don't do it. So for example, here's a picture from Prince of Persia, right? So they had some stuff that they built up somewhere in the desert, and then they, there's some dividing line right here. You can see that they extended this thing to have a ladder and a roof, but the brown between what you want to keep and the brown between what you want to throw away are very, very similar. Yeah. There's really nothing, I mean, the humans do, but there's nothing automatic that will do that kind of thing for you, right? Exactly. What is sharp and what is blurry? I mean, there are some tools, like for example, your Photoshop has this kind of intelligent scissors, right, that will help you crop out something from the background. And those are the kinds of algorithms that I talk about in terms of how do you do that intelligent scissors. But realistically, no one is really using that stuff on a regular basis in Hollywood because it's just not very procedural. Like you can't have a one-size-fits-all solution to that problem. And the time that you spend taking the output of your automatic algorithm and fixing it is not that different than the time you'd spend if you just did it yourself totally manually, right? So that's where hopefully there would be a balance one day, but we're not really there yet. Okay. So once you've got these pieces that you've taken off of various backgrounds, you want to put them back together into a single compelling scene. And actually, this is the chapter that I circulated around for the seminar. So this is some pictures according to that. So that process of putting stuff back together, I would call compositing, okay? And so, or I'd say image editing and compositing. So in editing, for example, I want to take maybe a single image, and a very common thing is to remove stuff that you don't want, right? So you want to remove these wires and gantries that are holding up these actors. You want to remove this thing, which is maybe some sort of a counterweight or something, pictures of cameras and crew that are in the background. And so, again, there are parts of this problem that are easy and parts of it that are hard. So maybe, for example, here, filling in some texture behind this wire that looks like the ceiling, or I guess maybe this is the floor of Inception, maybe that's not such a hard problem because that's a relatively constant color, or maybe it's like a smooth gradient, right? One issue, though, is that you have to make sure that filled-in texture looks good as you move it throughout the video, right? And that's a big problem, is because you can imagine that you look at a frame, you wouldn't be able to tell anything is wrong. You look at the next frame, nothing is wrong. But when you play those frames together, you see there's some weirdness in that region, right? And they used to call that the glass rod effect because it looked like you were waving a glass rod in front of the camera. Something was off, right? That's someone commented this in their questions that they submitted to me. You can just tell something is perceptually wrong, right? And that's a problem where, again, there are lots of people who are, just jogging their dial back and forth on this video thing, making sure that you don't see any wiggle or jiggle in the stuff that is painted out, right? So there are some semi-automatic tools, like for example, if you've ever used Photoshop, there's stuff like the clone brush and stuff like that, they call it. And again, those work very well on still images, but on video, it's still a long way to go to make that look really good. Here's another example of removing stuff. So the end of source code where they're reflected in this bean sculpture in Chicago, and they have to remove the population that's watching what's going on and this camera crew in the reflection, right? So it's to paint in stuff behind there. Again, that's not really such a hard problem because what they want to paint in is fairly, constant color. Here's an example of, from The Mummy, right, where you got these green-suited guys. You want to paint them out, paint in the realistic-looking background, and replace them with something that looks like this, right? And so again, here, you may be able to leverage, for example, in a situation like this, the fact that you could take a picture of the scene without the people in it and use that to help you fill in the pixels that you know. So any tricks like that that you can use, even if you don't necessarily see the scene from the right perspective, you may be able to kind of warp in some texture from some other frames of the video sequence or from some other camera to fill in stuff that looks good. Okay, so here's a shot from Moon, right, which is a good movie. And so here again is a situation where there was not really a lot of blue screen or green screen used on this movie, especially in the shots where Sam Rockwell is interacting with himself, right? So he did, one side of the scene in one take, the other side of the scene in the other take, and those two takes have to be stitched together seamlessly to make it look like it was one single shot, right? And so again, I talked about that a little bit in the chapter that I circulated. So the question is, somewhere here is a dividing line between the two videos, and the goal is to make that be as imperceptible as possible. So when I was, growing up, I was watching movies like Back to the Future, right? And so in situations like that where Marty McFly is interacting with himself, those days, first of all, it was more on film than it was on digital, but you would usually see there would be like a big, fence or a log between the two sides of the screen, right? These days, it's much more subtle. I mean, even in the latter days, like on Friends, right? There was Phoebe and her twin, right? There wasn't necessarily like a big dividing line between all those shots. And so there's a question about, basically where do you draw that line? Sometimes you want to draw it through places like edges where you're not going to notice the difference, right? So maybe I follow something along the pathway of this door and around the corner of the ping pong table. Or maybe I, could cut through some empty region where the pixels are going to be so similar anyway, and maybe I do a little smoothing across the seam so you don't notice the difference there. And so again, that is also a very expert by eye judgment made by compositors. But there is a lot of hope for computer vision to actually help solve that problem automatically, finding a good path that is imperceptible. Here's another example, right? So some of these Harry Potters are probably done on blue screen. Some of them were maybe in the scene, or maybe they were all on blue screen. Really hard to tell. So the question is, how do you divide them up? And then, of course, not only do you have to put them back in, but you have to put them back in at different depths, right? So for example, this person is standing in front of that person, so you have to layer these pieces that you're putting back into the world. And again, a single frame from some crazy Hollywood movie like Transformers probably has like tens or maybe even hundreds of depth planes of stuff that is all stuck together. So if you ever watch a behind the scenes of some DVD, you'll see usually these making of shots where you see all the stuff stacking together to make the scene that you see. Here's an example from an early Michel Gondry video with Kylie Minogue, right, where she's walking around the same scene, interacting with herself. And I think that this is actually not a blue screen shot at all. She probably did 4 takes going around here, and they had to do some crazy compositing to pull her off and put her in the right place and keep the depth ordering straight and all that stuff. This is a great video. Again, so here's an example of, again, this is the movie called The Road, right? So this post-apocalyptic America where actually there is this is apparently a region, I think of somewhere in Pennsylvania that was flooded out or something and basically abandoned. So some of this was real environments that they dressed with some beat up cars, and then they took another street in the same neighborhood and flipped it and then put it on the other side of here, right? And so somewhere here there's a dividing line between real and imaginary, and then there's lots of other stuff that's been stuck into the scene, right? Like there's debris and smoke and stuff like that. Those are all different layers. Let's see what we're gonna look at here. Here's an example of doing it with video. So this is a famous fight between Muhammad Ali, I don't remember who the opponent was, but here they've substituted the opponent with his daughter, right? Who is clearly, couldn't have possibly been there in the scene, and it looks like they're boxing each other, right? So here's a case where, she's probably, maybe she's in the boxing ring, maybe she's on a green screen, and they have to make it look not only like she's in the same space, but also they have to do kind of some processing of the video to make it look like that video was from that era, right? So pretty clever. And here's some examples from Transformers. So, I like this. The guy with the barbecue tongs turns into the robot, right? And so they have to paint out the tongs and substitute in the robot, right? And here's another example from the same movie where they give Ken Jeong this blue head on a stick to react to, and then they have this blue thing that they mush up against his head to move his glasses around. And so in order to put the thing in, they have to kind of paint in, what is the realistic looking hair and glasses that you didn't see behind the blue thing, and then put in the alien, right? And here there are different steps of, putting the goo in the alien's mouth so it looks good, right? So there's lots of kind of stuff that they're painting out and putting in scenes like this. I like the part where they're pushing up his head with the blue thing, right? Yeah. Because again, making a computer graphic Ken Jeong whose skin deforms realistically to being poked with the alien, it's cheaper for them to do it with a blue stick than it is for them to develop a really complicated head model that reacts naturally. Okay, so now let me talk about how do we put these monsters into these scenes and make them look realistic, okay? I fear I'm going a little bit over time here, so let me pick it up a little bit. Okay, so certainly in all these blue screens and green screen stuff that you see a lot of pictures of studios like this that have lots of masking tape crosses and stuff, right? And they use these crosses to track how the camera is moving, okay? And so you'll see pictures like this or like this that you've got a bunch of different stuff, and that's what the camera is going to kind of grab onto to figure out, otherwise I don't really have any sort of depth cues for if the camera's moving around a blue screen, right? I don't really know how far away it is from the actors necessarily. I want to get some sense of where that camera is moving in 3D space. So sometimes they will do things like this in a set where they'll put artificial markers. Sometimes they'll have a real set and they'll plant some stuff, right? For example, here you've got these red dots that are going to get painted out later that help them know how the camera is moving with respect to this environment. Here they've put red, kind of crude red, patches on this horse because they're going to add in the Pegasus wings later on. Or even for a movie like Black Swan, right? Here they put these dots, tracking markers on Natalie Portman's arms so they could know how to add in the realistic looking feathers later. Here's another example from Terminator. Now, if you don't have the ability to put tracking markers on people or objects, then you have to use kind of pieces of the scene that you can naturally kind of track as the camera moves. So for example, this is, I believe, I want to say it's in Monaco or Monte Carlo. This is from Iron Man 2, right? The big race with Whiplash. And so here, they want to make it look like there are more boats in the marina and more people in the stands. And so what they do is they will track, pieces of the scene. For example, maybe they'll track like the end of this red and white stripy thing, or the wheel of this car, or the front of this bus. And then they'll use that to help them infer the motion of the camera in order to put things in, like the rest of the boats, that seem to move along with the camera. And so that feature tracking problem, again, you can kind of bring that back to like kind of a perceptual organization or a perceptual importance problem of what kinds of things are good to track in a scene, right? Flat patches of asphalt are probably not great because you really can't distinguish one patch of asphalt from another. But things like corners, like the corner of this red and white stripy thing is a fairly unique thing because it's got a lot of edge information in both directions, so it's a good feature to track. And of course, any movie like Transformers or even G-Force, where you have animated objects that are interacting with the real world, you're doing this kind of real world tracking all the time. And here's an example just of, there are some triangle marks on the blue screen, and they use that motion to help figure out when they transfer over from the guy who is running, and then you can see this guy just kind of like falls onto a mat, and at some point in the middle, they turn into the guy on the light cycle, right? But this feature tracking is what they need to help them figure out, three-dimensionally, how are things moving. So sometimes you're just tracking like just little bits of scene, like a triangle or a cross on the wall. And sometimes you want to track everything that's happening in the scene. So for example, there is an otherwise kind of cheesy movie called What Dreams May Come, right? Long ago, Robin Williams movie, where he dreams that he is in one of his wife's paintings. And so for chunks of the movie, it's like he's moving through an oil painting, right? So here's a kind of an example of him sliding through this kind of oil painting-y environment, right? And so to do this, they had him walk through a real kind of lush, foresty thing down to a river, and they had to track, okay, for every pixel in that scene, how is that pixel moving so that I can add a little bit of a smear to it that looks like an oil painting, right? So that's, again, an application of what I would call optical flow, right? So if I know the optical flow vectors, I can kind of, blend the scene in the directions of these vectors to make it look like there is this kind of a smooshy effect. Another use of kind of dense correspondence between objects is morphing, right? So in the mid-90s, there was a spate of morphing, right? This is the Michael Jackson video that kind of started it all off, right? Where you've got different faces that are kind of transforming into each other. And for that, you need to know exactly how one person's eyes, nose, and mouth and the rest of their head is matching to every pixel of another person so that they can do this kind of even blend, right? And even at the time, I mean, I don't think that morphing has gotten a lot better than this. It's still a very compelling effect. And so this is the kind of thing you can do these days, kind of on your desktop in MATLAB, and it will look pretty good, actually. Again, the fact that it's video and the fact that there's like people's different facial hair and stuff like that, a lot of that stuff is put in after the fact. But the face-to-face transitions is actually pretty smooth. And of course, they use the same thing in Terminator 2 and stuff like that, right? So I remember when I was a kid, they played this after The Simpsons one night, and it was the first time that anyone had seen anything like this. It was just like really an amazing thing. I never had seen anything like this before. It was very slick. So, okay. And again, one of the other reasons why you want to know where every pixel is to help out with that painting out unwanted objects problem. So this is a scene from Deadwood where everything is gray except for the modern day traffic light in the middle. And so they they move the camera around to see what's behind it in order to help figure out what should be behind there. Another reason for optical flow is it's very common to retime a scene. Things move too fast or too slow when they're filmed, and you want to change them up, right? So one example is in things like, you want to have this kind of slow-mo fighting, or this is a scene. I had to find a better example of this where you've got, like some sort of the effect is like a very high frame rate camera, but maybe you don't have a very high frame rate camera. You actually want to take the action that you filmed and slow it down and fill in realistic looking frames in between the frames that you actually got, right? That's an application of optical flow as well. And it's used very commonly to, maybe the director needs a 3.5 second clip, but they actually only have a 3.3 second clip. So how do they fill in those frames? They do it by frame interpolation, right? And a lot of correspondence comes up in stereo filming these days, right? So this is a scene from Transformers where you have to have kind of good correspondence between the left and right eye in order to make these compelling stereo effects. So once you've got all this correspondence, then you can start to do things like say, okay, here is the real scene that was filmed, and now I can start to put in artificial objects into the scene that look like they are hanging in space or grabbing onto the scene in ways that look totally natural. So now I can put these alien spaceships here, and after I've figured out how the camera moves, I can put those spaceships in the three-dimensional space of the world in a way that looks totally, well, such as it were, totally realistic, right? And this, again, is a fairly common thing to do, certainly, for putting monsters into, movies that don't physically exist. But here's an example of test footage, right, where you got your standard shaky camcorder, and they are putting this car into the parking lot. And by the time they finish putting the car in, it looks just like the car that's sitting behind it, right? But you probably would not have thought twice about that car being in the parking lot, right? So for example, for not only things like Transformers, where there are lots of fake cars, but also like car commercials. How often do you think they actually have the real car in the car commercials that you see? Answer, not very often, right? Those cars are mostly computer generated, and they look really good, right? So again, you really can't trust those kinds of things that you're seeing. Here's a great example of putting in a effect in the real world that, they're overlaying this footage onto, this is a movie called Stranger Than Fiction that I like a lot, where, there's this kind of GUI interface that's being superimposed on this guy and behind this guy, and they use camera tracking to make sure all that stuff kind of looks like it's sticking to his tie and sticking to his closet. And there are lots of very nice, subtle effects in the beginning of this movie that are kind of good uses of match moving. Like here where he's kind of, the idea is he's kind of like an OCD guy, so he's counting the steps on the ground. You see these things are lighting up as he hits them, right? And these numbers look like they're hanging there in three-dimensional space. So yeah, so that's kind of a slick use that doesn't involve aliens or anything like that. Or here's the credits for Easy A, right? A teen movie that you wouldn't have thought had any visual effects in it. But again, they have to know how the camera is moving in order to make these credits seem to stick to the ground and have the students pass in front of them in ways that look natural. So it's, again, a very subtle effect, right? Your eye starts to pick up these credits as they move around the scene, and they look like they belong there, right? So if you start to look for this kind of credit gimmick, they use this in a lot of movies. They use it in Zombieland. They use it in Fringe, right? All sorts of TV shows and movies have this kind of thing. And so these days, it's very common for the first time that a shot arrives at a visual effects facility, they will just figure out how the camera moved in the scene, just in case anyone needs that information later. Maybe they'll use it, maybe they won't, but this is like a very common first step. And even in scene, you know, series, this is the Russell Crowe movie, A Beautiful Mind, right? So another reason they'll do match moving is to do set augmentations, right? So they'll film on a set, then they'll add stuff to that set to make it look realistic. So this is actually what the set looked like, right? And they filled in all this stuff after the fact, right? And of course, this is actually a video of pushing in on the window. And so they reconstructed the rest of this Princeton, you know, environment from footage they took on campus, right? But Russell Crowe wasn't actually ever sitting in this dorm room anywhere. Okay, so two more things. One of them is motion capture, right? Which is probably the most familiar thing to most people who know something about visual effects. And so I got a lot of help from John. When I was working on my motion capture chapter, I went to the Winslow building and got suited up in the suit, which I'm not going to show you here. You know, this is kind of the popular conception of taking the person in the ping pong ball suit, and this is an example from Iron Man, you know, mapping the ping pong ball person onto the animated character, right? And so certainly this kind of came into the public consciousness with the Gollum character from the Lord of the Rings trilogy. These days, of course, Avatar was also a big motion capture thing. So here, these people were performing not only with the motion capture suits, but also with these cameras that were looking at the dots on their faces for doing some facial motion capture. And then that turned into these very realistic performances. But let me just say that the popular perception that you take the motion capture data and you just turn the crank and it turns into a beautiful animated character is really far from the truth. The movie studios and PR people would like you to think that that's true, but it's really not the case. So there's a ton of animation that goes on top of these capture performances. Part of the reason is that the data that they get from the system is not always as accurate or as useful as they would like. Part of it is that maybe they want to change the performance of the character after they've collected the data. Maybe they want his arm to be over here instead of over there, so you have to actually modify things. Part of it is that even though they have the data on people's faces, it's still very difficult to capture accurately, for example, the lips and the jawline and stuff like that, or the eyes. They don't put any markers on people's eyeballs, right? So all that stuff that really gives this human dimension to the performance is probably hand animated, right? And so there's definitely a kind of a kerfuffle on Rise of the Planet of the Apes, right? Where there was some talk, you know, should Andy Serkis get an Oscar nomination for his performance? You know, no doubt that was a huge factor in how they used, what they used to animate that Caesar ape. But at the same time, there was like a ton of hand animation, keyframe animation done on top of that video, to the extent that sometimes, you know, when you take motion capture video of an actor, sometimes it's only used as reference, which means the animator's literally kind of just flipping back and forth between the video and their animated character, but they're not actually driving their performance with those motion capture dots. So you should kind of take some of this mocap stuff with a grain of salt when you read about it in the popular press. This is an example of Iron Man. So again, there's a story about Iron Man 2 where apparently towards the end of Iron Man 1, they realized, even though they did have the Iron Man suit on Iron Man 1, the whole thing, they realized at some point that they could kind of get away with this with Robert Downey Jr. So he wouldn't have to put on the whole thing every morning, which would obviously take a lot of time, and the whole thing weighed a whole amount. But they didn't tell Don Cheadle that, you know, when he came up for Iron Man 2. So, you know, Don Cheadle shows up in the whole War Machine armor, and Robert Downey Jr. is wearing the red pajamas like, you know, you're a sucker for putting on this whole thing, right? So these days, this is a special thing called iMocap from Industrial Light and Magic, where it's not exactly a motion capture suit. It's kind of a pattern marker suit. And if you watch like the behind the scenes of the Avengers, you see they've kind of updated what that suit looks like. Now it's kind of like a gray bodysuit that has a bunch of triangles on it. But it's a little bit less of a imposition than having to wear a very carefully calibrated ping pong ball suit. You know, here's an example of the iMocap system in action with the Davy Jones character from Pirates of the Caribbean. And the advantage of this iMocap system is they don't have to actually film the actors on a soundstage. They film them in the real environment, and then they put in the animated character. Now again, it's kind of unclear how much of this, from this video, it's kind of unclear how much of this is keyframe animation and how much of this is driven by mocap data. And of course, no one will ever tell you exactly what was what, right? But it's still very compelling. I just played this video game, L.A. Noire, right? So L.A. Noire had a lot of facial motion capture that they kind of apparently didn't do a lot of editing on. They just streamed it right into the game, and it looks pretty good. Here's just another example of a guy in a motion capture suit that turns into this. Tron Legacy, you know, was known for having this kind of motion captured Jeff Bridges, who turned into a younger version of himself in this grid environment, right? So he was wearing, at various times, a motion capture suit, a helmet that had these carbon fiber rods looking at this pattern of dots on his face, and these are kind of some of the steps, right? So there was a person on the set who was like the Jeff Bridges stand-in, and his head was replaced entirely with the CGI Jeff Bridges head that was driven by these Jeff Bridges dots. And so here's a little bit of a video of how that worked. So here you can see there's a combination of, you know, the guy over here in the suit, Jeff Bridges doing the same motion, the various iterations of the Jeff Bridges CGI younger head, and then they have to stick that back onto the collar line of the real person. So this part that's now included here is probably the real guy, but the head is CGI, right? So, you know, people argued about whether this was a good-looking effect, but I mean, there was a lot of effort that went into making this come together, and I think that for what it was actually pretty good. The same people were involved in, for example, the Curious Case of Benjamin Button, the kind of Brad Pitt aging effect was done by the same company, Digital Domain. And you know, people say that, you know, you can complain about this, but you would probably be surprised at how many digital doubles there are in movies, right? For example, the last shot of Spider-Man 2 with Dr. Octopus kind of floating down into the water after his reactor has blown out, that's an entirely CGI human, and you would never think twice about it, right? That's not to say that it was all totally hand-coded. They get these very nice human models from doing laser scans of people. That's the last thing I want to talk about. Oh, there's just one thing. They do motion capture on animals, too. So here's motion capture on a horse for Avatar, right? Of course, you need a much bigger motion capture studio than the Winslow building to be able to do this. So here's something that is a little bit closer to my research area, which is 3D data acquisition. So here you recognize the Green Island Bridge, right? So here is our LiDAR scanner that we have. This is basically like a souped-up version of the Home Depot laser rangefinder that you get, where basically you bounce a laser dot off a surface, and it comes back and tells you how far away that surface is, right? And so we do this to acquire very high-resolution laser scans of our RPI campus, right? So here's an example of the VCC that we took a few years ago. And, you know, the resolution of these scans is pretty good. You know, I would say it's millimeter accuracy to the level that you can get, you know, kind of details in the brickwork of the buildings and stuff like that. It doesn't always do a good job with things like windows. You can see there are holes in windows. Like we scanned the MPAC building a few years ago, and lots of the laser rays just went right through that big glass surface in the front and hit the big concert hall inside. So it's very tough to get scans of glass objects. But people in Hollywood do this routinely for movie sets. So every movie set that they build, they will take in a similar scanner like this, and they will acquire three-dimensional data of it, and that they can use that information for you know, making a virtual model of it. They can use it for extending the set for pieces that they didn't capture. So this is an example from the most recent X-Men movie, right, where the young mutants were held in this facility and they broke out. So this is from Thor, right? So for Thor, they built this whole New Mexico small town where a lot of the action took place, and they laser scanned it. So they had very accurate models of all the buildings and all the trees and all that stuff in that environment. And so routinely, you know, they will call in a special visual effects company to come in, scan this stuff, and then send it off to the people who are doing the effects. And so I got to say that, I'll show you some more pictures. So not only do they scan sets, so here's an example from, I think, Battle of Los Angeles, right? Freeway with lots of cars. And so this is good just to know, you know, where were those cars, right? Not going out with a measuring tape and figuring out what orientation and angle all these cars were at. Instead, you take a laser scanner and you do it and get this very accurate 3D information. They'll scan things like, you know, these are the ships from Pirates of the Caribbean. Cars, these are cars from Fast 5, right? They will take, you know, very accurate laser measurements of all the vehicles, cars and trucks and trains and support vehicles and stuff like that. And again, you know, shiny objects are not really good for laser scanning. And so sometimes what they may have to do is they may have to actually put a very fine powder on these shiny objects in order to get a good return off a laser scanner. So you may take, you know, you may drive up this beautiful, like, beautiful new black, you know, Chevy van, and then the laser scanning guys want to just crap it up with, you know, white paint and stuff like that. So there's a tension between the guys who need to do the scanning and the guys who don't want to screw up the props. Again, every prop, right, that you will see in a movie is just scanned as a matter of course, right? So these are some swords and jetpacks and stuff from, I think, Sucker Punch. You guys probably recognize this helmet from the Avengers, you know, dinosaurs and things like that. And they also scan people, right? So every actor is laser scanned with this kind of a laser stripe system where this is like a structured light system, for those of you that know what that is. Basically, these laser scanners go up and down. They cast a stripe on the body of the person being scanned, and then cameras record how that stripe deforms, and then they use that as the basis for building up very accurate 3D models of people. And so here, young Harry Potter being scanned by the system. I guess you can scan other things besides people, like this big statue from one of the Mummy movies. But these are the kinds of results that you get, right? So fairly high detail scans, and they use this, again, for making very accurate digital doubles of characters for stunts that you couldn't actually put a person in, for example, like Neo, fighting all the Agent Smiths, right? There were lots of digital Agent Smiths in that movie, and there was lots of digital Neo also, right? So these days, again, sometimes it's very difficult to tell whether you're looking at the real actor or whether you're looking at a very convincing laser scanned, animated digital double. And so Jack Black, Emily Blunt, Scott Glenn, again from Sucker Punch. Again, you get very detailed stuff. It looks pretty good. I mean, the hair can be a little bit wonky, but usually they're doing it to get the very accurate facial capture. And they have special systems if you really want very specific head motion capture. They'll put you down in a chair and do a very accurate head scan. Ryan Reynolds, an embarrassing picture of him. These are the frost giants from Thor. And again, very detailed, very accurate. And so I gotta say, this is one of the coolest places I've ever been to. So this is a company that just does custom laser scanning of sets, props, and people. And so, you go into this place, it looks like it's a really sketchy neighborhood. It's one of those kinds of buildings that has like the totally blacked out windows. You think you're gonna go into some sort of like dangerous warehouse situation. Then you go in and it's got like, it's like a candy store of all sorts of, I don't have enough time to show you all the pictures I took at this place. But they've got like things from, like miniature heads of all the people that they've ever scanned in a little, like each one is about the size of an egg in this big display, to, action figures, to big busts, to the kinds of scale things that you would see at like Comic-Con, right? They're the ones who make these huge Lord Voldemorts and avatars and stuff like that that you'll see on showroom floors. All that is done from these laser scans that they produce. And so not only do they scan things for movies, but also afterwards they use the same scans for making action figures and video game tie-ins, right? So all this data is really used all the time now in Hollywood. That's probably why action figures look a lot better now than they did when I was a kid, right? Because they're coming from these lifelike scans. And so, yeah, that was just like one of the coolest places ever to go. All right, so I've gone a little bit over time, so I will conclude. So like I said, I wrote a book. So if you're interested in that, there's a copy in the library, should be, and so you can take a look at it. Also, like I said, take the course next semester, or hopefully whenever it's offered, if you're interested in learning more about the details, which I totally glossed over, about how all this stuff works. And with that, I will open it for questions. Right. So I don't want to assume that people know a lot about computer vision to begin with. So you don't have to know computer vision to be able to take the course and do well in it. Mathematically, I think that you want to have, you want to be able to do some calculus, take derivatives and set things equal to 0 to get minimum. You want to know some linear algebra, right? So matrix manipulations. And so if you've had kind of like the, multivariate calculus and matrix algebra course, that's okay. A linear algebra course would be even better. If you know something about image processing, like if you know how to use Photoshop, and know how pixels move and what they mean, that's also probably pretty good. So I would say, for most of what I do, linear algebra is the most important thing. And so, I had a mix. I taught this course once. Well, actually, I taught a version of this many years ago with Eric that was just basically reading a bunch of papers stapled together, and that's what kind of led me to believe that I should be writing a book about it instead of handing out papers. And that course had a real wide range of people in it. I mean, there were people from EMAC and arts. There were undergraduates and grad students. When I taught the course from this book the first time, it was mostly ECSE and CS grad students and undergrads. But the undergrads who didn't really have a ton of background did just fine. So I mean, we'll definitely get into lots of math. The course will be mostly me showing you the mathematical basis for a lot of these things. And then the way I like to handle it is basically, maybe a few homework problems for every kind of key concept, but then I want to have kind of like a culminating project where you apply several things that you learned in the class to make your own kind of like 30-second music video or special effects video, right? Where you either write code yourself or you piece together code that you find on the web and have to write some code to stick it together, right? And so that would be the kind of the culminating project of the course, right? And there may be some programming too for those, but I'm not really picky about the language that you program stuff in. So if you're doing it in Python or MATLAB or C, you know, I don't really have any preference as long as it looks good. So, yeah. Yep.
So for all these kind of technologies you're talking about, there's a lot of applications like security or
Mhm.
or medical
Yep.
research.
Yep.
Just curious about where, like, which of those applications is kind of driving the technology? Like,
Mm.
where exactly supporting the making of, new laser scanners?
Right. Well, you know, I think that a lot of the fundamental image understanding stuff probably was initially funded by like the NSF, kind of like big picture, broad science. Some of the stuff that is more like laser scanning and tracking and stuff like that, it's probably fair to say a lot of that came out of the defense community. You know, some of my research has to do with kind of more like security and surveillance type stuff. You know, health care and health services has driven a lot of stuff, as you know, like for example, a lot of motion capture stuff really came out of people who wanted to do orthopedics and medical diagnosis of are people getting better as we give them some sort of treatment for their walking disability, right? So I would say probably, you know, it's a mix between what I would say NSF, NIH, and DoD, with kind of a little bit more, you know, maybe a little bit more DoD these days than there used to be, but I mean, still lots of people are doing fundamental science funded by the NSF. And lots of people, you know, the nice thing about SIGGRAPH is that, you know, a lot of those people are producing just like super cool looking stuff that seem to have no real practical applications, and I don't know how they're funded. I mean, I think that many of those people are probably funded by NSFE kinds of awards, where it's just like exploring the limits of creating good computer vision algorithms and creating new computer graphics algorithms. So it's not all Big Brother, you know, some of it is. Yeah. What else? Yep.
How's the progress going on solving the uncanny valley?
Yeah, the uncanny valley. So it's easy to pick out when it's not working for sure, right? But I guess like I said, you know, it's getting a lot better in terms of you definitely have seen in movies, you know, heads and bodies of actors that were not really the actors that you think they are, and you never thought about it because they move the right way and they look the right way, right? To the extent that it's actually, I think, getting to be a concern for actors to be able, you know, to think that their performance could be modified or even replaced later on with a digital double that purports to be them, and they never had anything to do with it, right? So there's a story, and this was already like, you know, 10 years ago, where like these days, certainly modifications like tears, right? You know, people crying in movies, a lot of that is digital tears, right? And so apparently there was a sappy movie with Keanu Reeves and Charlize Theron where he was supposed to cry at the end, like Sweet November or something like that. So, and he was mad that they had basically interjected, you know, these fake tears into his face that he was never crying, right? Now, so I think that, you know, definitely in lots of movies, digital head replacement and stuff like that, like they will combine different heads from the same actor on different takes into one performance, right? In such a way that you won't see where the dividing line is, right? So if they like the way he smiled on this beat of a sentence in one take, but the way he was looking this way in the other take, they will put that stuff together. And so you could argue that that's kind of a fake thing, right? But they are getting better and better. There was, you know, there's this group in UCLA that has this digital light stage where they will take actors. So in addition to doing like this 3D scanning, they will also put actors into this, basically it's a half dome that has lots of cameras and lots of lights. And they will illuminate the person at a rapid speed with different combinations of lights from all these angles in order to know how their skin should look under different lighting conditions. So that you can make a very accurate looking facial model that reflects light, because you know, your skin is a really complex thing, right? Light doesn't just bounce off of it like it's a piece of plastic. You know, it goes in to some extent, there's this subsurface scattering on your skin. Your forehead is shiny because it's got oil on it. And so they can now take actors and by putting them in this light stage, make very convincing, you know, digital doubles. I think the hardest problem, I think, is not still images, but things like animation, making sure that those people move in a very believable way, right? So, you know, I think that you could argue that there are, you know, it'll be interesting to see, for example, like, what's a good example of a movie where they had an entirely digital human recently? You know, there's like, I guess they did a little bit of that, like in X-Men 3, where they had the younger Charles Xavier and Magneto talking to Jean Grey in her house, right? So that was kind of a combination of real actors who had this kind of smoothened head put on. I mean, Jeff Bridges from Tron Legacy is probably the best example. But I'm willing to bet that you will see stuff like that. So the other reason that Jeff Bridges had this uncanny valley problem was that it was not meant to be, so it was meant to be young Jeff Bridges, right? And so people know what young Jeff Bridges kind of looked like, and they also see regular Jeff Bridges in the same scene, right? So it's easy to compare them, right? Whereas if you're never really in on the joke that this is not supposed to be a digital character, you might not give it a second thought, right? And so that, I think, is where things are going, is that you will not even know that there's supposed to be something going wrong, and then your visual system just kind of compensates for it, as long as it looks kind of accurate. So I would say, you know, digital humans are definitely coming down the pike in animation for sure. And then that will raise lots of questions about, you know, right. Well, pictures, someone mentioned this in one of the grad student questions. I mean, like, still pictures, I think now are totally unreliable. I mean, like, you know, in terms of issues involving like photographic evidence, it's really up in the air in terms of whether you could trust a picture that comes to you as being tampered with or not. To the extent that now there's kind of like a, you know, a not counterintelligence, but, you know, a counter synthesis group that is basically trying to tell whether a digital image has been forged or not, right? For the purposes of exactly stuff like this, you know, is it legal court evidence? Was this person actually in this scene doing that thing, right? And so there have been some interesting papers in how can you tell whether a photo has been tampered with, like they say on Reddit, you know, I can tell by the pixels, right? You know, so, you know, for example, but they mean things like, you know, is the JPEG compression consistent across the whole image, or is there a region where the compression is not consistent with the rest of the scene, right? Is the noise grain of the camera the same across the whole scene, stuff like that. But yeah, it's really getting very difficult to tell. Yep. Yeah, so Final Fantasy, right. 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 So Final Fantasy, I thought that the lead character looked pretty good. I mean, I thought that was a pretty good effort, but some of the other characters were just like really robots. But the one that they put all the effort on, the lead Aki character, I thought that was a very nice example. And that was, you know, already 15 years ago, right? So, yeah. I mean, but the thing to remember is that, you know, if you throw enough money and throw enough person hours at the problem, you can get things that look really good, right? And so I think that the company that kind of supported that movie had a lot riding on making it look good, so they really put a lot of effort into that character. But these days, visual effects is on a super time crunch, and so, you know, you can't afford all the people that you might need to make the movie look, you know, 100% great. So sometimes when people criticize a movie for being crappy visual effects, it's not necessarily the company's fault who made the visual effects, it's that they had all sorts of bizarre constraints that they just couldn't do what they needed to do on the time frame that they had. I mean, without going off on too much of a tangent, the visual effects, even though you think that, you know, almost all of the popular movies or the high grossing movies these days are visual effects driven, right? Every frame that goes by has some sort of effect in it. Yet visual effects companies are really on the rocks. I mean, their profit margins are incredibly narrow, and they are, you know, paying for the movie that they're on with, you know, hoping of getting the next movie. I mean, and very venerable visual effects houses have gone out of business in recent years that seemed like they would never die, right? And so even though these movies do super well at the box office, that does not trickle down to the people who are actually doing the work that makes them palatable to the public, right? So it's a very strange problem. So you shouldn't think that all these people at ILM and Digital Domain are rich people driving around their Mercedes. It's not like that at all. Yep. Right. Right.
But are there any movies today, sort of like the really sort of, I would regard to be more literary movies that just completely reject? You mentioned Eastwood, like
Winter's Bone, right?
Why the heck would you
Right.
compete for that?
Right. I'm willing to bet there were visual effects in Winter's Bone for sure, right? I mean, you know, certainly compositing in things in the scene that weren't there. Like, for example, even just something as simple as, you know, the icy breath that looks like someone's in the cold, right? That stuff is digitally generated these days, right? And so just subtle stuff, right, that you wouldn't think was an effect is actually done all the time. Now, I mean, and the other thing that makes it, you know, one of the good news in some sense maybe is that now it's much more possible for an average person to make visual effects on their own, right? Like you can buy a copy of After Effects, you can buy a $400 green screen kit to set up in your basement, and you see people on YouTube doing things that look pretty good, right? I mean, so like if you look at the blog that I'm following here, you know, like there was a guy who did this Portal video, right, where he was basically making these, you know, portal gun effects, you know, he filmed it in his house. He did the effects on his own computer. You know, if you spend enough man hours on it, you can get stuff that looks pretty good, right? So, so the bar is lowered for people doing it on their own. I don't know if anyone, I mean, you might find things at Sundance and so on that people are just kind of, they don't do it because they don't have the money to do it, perhaps. But, you know, it also, I don't have any idea how the bidding process works, but it may not also be as expensive as you might think for smaller things. Yeah.
So you mentioned usually he still did it for Flags of Our Fathers in some form.
Mm-hmm.
But it sounded like he's one of the purists.
Right.
So I wonder whether Unforgiven has
Right.
any special.
So that's probably a movie that was maybe shot on film. Right? I mean, the further back you go, the more you're in the world of, so there's a difference between visual effects and special effects. So visual effects are basically, the line is whether it's computer generated or not. Special effects are things like prosthetics and explosions and stuff like that. And of course, stuff like that is always used in movies like that. Now, visual effects, I would be surprised if there was maybe a lot of that in a movie like Unforgiven. You know, like I said, these days, there are lots and lots of, you know, small visual effects houses that get called in to clean up a couple shots here and there on all sorts of movies, right? Like I went to this very, you know, it's maybe like a 20 or 30 person operation who mostly did TV effects for things, but they did, you know, 4 shots of, you know, maybe 30 frames each for Avatar, and they did, you know, a few shots for this movie. So they had their fingers in all sorts of stuff, and these things get bid out to different visual effects companies on a shot-by-shot basis, and so maybe just doing a couple shots here and there isn't that expensive. The other thing that's kind of surprising is you might think that one company does all the visual effects for one movie. That's totally not true. If you look at the credits of any movie, right, you see like zillions of companies involved in a movie like Iron Man, right? And so somehow all those people have to work together to make all their shots come together in a harmonious way, which is surprising that it works the way it does sometimes. But still, it's a kind of a sign that visual effects people don't get that much respect, because those visual effects people will come after like catering, right? You know, and you know, drivers and stuff like that. So you know, it's kind of funny that they still seem to be on the short end of the stick in industry for whatever reason.
Do you happen to know about the Capital District movies?
Oh, you mean the one in Schenectady? Yeah. Yeah, I don't know much about those, right?
But wasn't Salt?
Yeah, so Salt for sure was an Albany thing. And I'm sure that in that freeway chase, there were lots of visual effects that were done on that, right?
Well, I was watching
Yeah.
her, they put her
On the truck, yeah. Right. Yeah, so there's an example of, I'm sure they had to paint out lots of wires and stuff for safety that was holding her onto the truck, right? And certainly there were probably cars and stuff on the freeway that were digitally added in afterwards, right? I've seen some video. I don't have all the videos here that I have in my library, but you know, like cars are very easy to make these days. So I mean, you can just kind of smack digital cars into a highway scene. You wouldn't even think that they weren't there in the first place, right? So I'm sure they closed off the freeway and just had maybe the 2 trucks, right, and everything else is digital, right? Yeah. Okay, thanks a lot. So I'll see some of you at 4 o'clock, I guess. Now you know. Yeah. So you learned something. Yeah.
Oh, just a lot, but I think you're really you're a star. And I'll only
Well.
say to you probably, I mean, the introduction he gave you,
It's
there
embarrassing.
will be one other major difference, I'm sure.
Well, we'll see.
Let's,
Knock on wood.
we can say.
Yeah. Yeah.
Anyway, it was just super.
Yeah. Thanks.
You know, I do a lot of photography, and the whole photographic field is really concerned with me, because now you can enter juried shows, and you
Yeah.
have to somehow attest to the fact that untouched.
Right.
And you know, does that include cropping, et cetera?
Oh, yeah. People
Yeah,
touch up
and
Photoshop stuff. Yeah.
Absolutely nothing.
Right.
Nothing done, not even cropping.
Yeah.
And then I have a friend who sells his photography.
That's great.
Yeah.
Thanks. I'll see you at dinner.
Sounds good.
Trip pics and all, I mean, $600, $1,000 type of stuff. Beautiful, beautiful landscapes. And he classically has done things, beautiful landscape. And there's a set of, let's say, boats turned upside down in the foreground, the
Right.
lakes in the background, mountains,
Yep.
and so on. And it's all black and white. And the only color is the bottom of the boats, which happen to be red.
Right.
Well, I just bought a little camera for my grandson, you know, and it has all kinds of programmable options. One of which,
Yes.
is called partial color.
Right.
What the hell is that?
Yeah.
I just tune it in,
Yep.
take a shot, and everything is black and white.
Yep.
And the red stick. I mean,
You could do it. Yeah.
and he can actually do it.
Yep.
Without touching it. To say nothing of, you know, what you pointed out, the smiles, and which kind of smile.
Right.
Group smile, single smile.
Right.
It's absolutely unbelievable. people
Yeah.
don't fully appreciate what it's all about.
Yeah,
And
it's
more to
crazy.
the point, they really don't seem to care how it's done. They just buy it, push buttons, and do it.
Yep.
And I think we're going to lose sight of some of the creativity,
Yeah.
originality, and how to go to the next step.
Right. Yeah, that's true. Yeah. All right.
Great job.
Sure. See you around. Hi.
Thank you. Yeah.
Thanks.
Question for you. Actually, there's several things. But one thing I want to point out is the moon there.
Yeah.
What's the director's
Yeah, yeah.
commentary? Right? That's pass.
Right.
The camera thing for that shot where they're both interacting.
Right.
Sam Rockwell. That was the one that was beautifully executed.
Yeah, yeah.
4 passes on the camera.
Right.
For that to happen.
Yeah, I read the, so there's a special effect, or kind of like a visual effects trade journal that I get, and reading that article is really interesting, right? Where, sometimes he puts his hand on the other guy's shoulder, right?
Exactly right, and that was
Yeah.
brilliantly done.
Yeah, yeah.
Other thing, though, the thing that was done at Carnegie Mellon, the mapping the
Yeah.
wireframe onto the face, actually somebody was developing an accessibility application. And that would be a useful thing to be able to do. And it is under
Sure.
controlled conditions where it's actually for kids who are quadriplegic and so forth. So they'd be in laptop camera
Yep.
looking at them. We could control through background,
Yeah.
within broad limits. But just getting some sort of a read on the lower part of the face to
I think that's very viable. Yeah.
Are those libraries available? How easy is it to get this stuff? Because
I think that you could probably.
that should be more of
So yeah, I mean, I can. If you email me, I can ping you back with some references. I mean, like, part of it depends on whether you kind of care about just like a 2D model, like the red masks on the people in the crowd, or whether you want a 3D model of the head.
Only because we're looking at gesture. These kids who don't have,
Right.
they're like, cerebral palsy, handicapped
Right.
in other ways.
And so their hands are involved also.
They're moving their head.
Right.
And of course, we already have this
Right.
happening.
Yeah.
This sort of thing. And
Right.
this sort of thing.
Yeah.
You could grab that.
Yeah, I think.
Eventually, also
Yeah.
eye blink would be handy to get too.
I have
They
to-
very, very limited range of motion. The idea is this is a musical application. They're actually playing music with this.
Right.
And they love it. They actually go crazy. This
Right.
only released 3. They go nuts over this thing.
Right.
So it's really effective.
Yeah, yeah.
For these kids to open up. So this is like the next generation.
Right. I have to imagine that there is some reasonable head tracking
Yeah, they'd have
that
to
you
do
could do.
something free,
Right.
like some sort of an
Yeah.
open source library, something that's super
I think.
something that doesn't
Yeah.
have to be super sophisticated. We're not trying
Yeah,
to
yeah.
make them look like,
Right. You're not trying to do anything. You just want to. Yeah.
right. It's just simply a matter of knowing what the head is oriented.
I have to imagine that there is some stuff that you could just kind of grab off of an open source library.
That would be great.
It must exist. It's not really my research area, but I'm sure we could find
Sure,
something.
I don't need,
Yeah.
again, it would be probably something that could be licensed to it if the need ever came
Right.
up. But right now, the answer is it's given away for free, so it's not like
Sure.
there's no business model behind this. It's just
Yeah. No, I think I'm